Hello, this video is going to be about momentum. So the momentum of an object is equal to its mass multiplied by its velocity. It's pretty simple. Velocity is a vector quantity, remember, which means that velocity can be positive if something is moving forward or negative if it's moving backwards. Velocity has a direction, and that means that momentum also has a direction. You can have positive momentum if you're moving forwards and negative momentum if you're moving backwards. So momentum is a vector just like velocity. The symbol for momentum is a lowercase p for historical reasons, and because m was already used for mass, so we couldn't use it for momentum. So this momentum equals mass times velocity formula can also be written like this. Momentum is equal to mass times velocity. The unit of momentum is kilograms times meters per second. There's not really a nicer version of it. It's because mass is in kilograms, velocity is in meters per second, so you multiply those two together, and you get the units for momentum. Momentum is important because, similar to energy, it is conserved within a system of interacting objects. That means that the total combined momentum of a system will never change over time. And that means that if you have some objects interacting, like for example a red, green, and blue object, their combined momentum will always be equal to the same number. So if at any single point you take a snapshot of your system and you add up all of the object's momenta, then you will get the same constant number. They can push each other around and the momentum will change. So for example, maybe there's an explosion in the middle and these move in opposite directions, like that. This guy will get some positive momentum, these guys will get some sort of negative momentum in the x and y directions, and they're all now moving, they have velocities, so they have different momenta than they originally had. But the total combined amount will never change. You add up all of the momenta at the very beginning, you get some constant number. Now the red momentum can change, the blue momentum can change, and the green momentum can change. They can all change, they all move. And they have new momenta, which are not necessarily the same as the old ones, so these don't have to be the same. Just like when you do the energy, the kinetic energy of an object when it rolls down the hill isn't the same, and the gravitational energy isn't the same. But if you add up the amounts, they're always going to be the same, because any positive change in one will cause a negative change in another. Now, if there are only two objects interacting, then if one object gains momentum, the other one has to lose momentum. This is going to be the situation you're in an intro physics class mostly. This means that the change of momentum of the first object is going to be equal to the negative amount of the change of momentum of the other object. In other words, if this guy gains positive momentum, then this guy must lose momentum because it's conserved. Now, technically, the change of momentum is equal and opposite for two different objects. The change of momentum is equal and opposite. This is why if a cannon shoots a cannonball forwards, the cannon will itself roll backwards, because the cannonball gets some positive momentum, and therefore the cannon must acquire some negative momentum. This is also why guns have recoil, meaning that they move backwards if you shoot forwards. If you hold a gun, and you don't hold it tightly, then when the bullet moves forward, the gun will move backwards. Rocket fuel moves downwards, and this causes the rocket to move upwards, because the rocket fuel is getting negative momentum, therefore the rocket must acquire some positive momentum to keep the total amount constant. And you will get the change of momentum by doing final minus initial. So I'm going to show you something that may look nasty, but I will simplify it for you. You have the final momentum of an object minus its initial momentum. So this is for the first object, maybe this is the cannon. That's equal to the negative final minus initial momentum of the other object. Maybe this is the cannonball. In this class, we are almost always dealing with objects that are not moving at the beginning. For example, when you have this cannon. The cannon is not initially moving, it's initially stationary. So is the cannonball. So the initial momentum is 0. Then the cannonball gets some positive momentum, and the cannon gets some negative momentum. But initially it's 0. So if you have this formula, but the initial momenta are 0 because they're not moving at the beginning, then this simplifies. This goes away, and this goes away. And all that happens is you have the final momentum of the first object is equal to the negative final momentum of the second object. And this is going to be a formula that you use in most introductory physics classes, because it's pretty simple. So normally, it's the case that one object's momentum is equal to the negative other object's momentum. Because when this guy moves forwards, this guy has to move backwards. This lets us figure out how objects interact. Now, all the previous slides can be summarized with these equations. Momentum is equal to mass times velocity, always. The change of momentum of one object is going to be equal to the negative change of momentum of another object that forces it, pushes it. And this is going to be true if you only have two objects. Finally, this last one, where the momentum of one object is equal to the negative momentum of another object, is going to be true if you have two objects and they are initially stationary, so they're initially not moving. This is the simplest version, and we're going to be using it mostly. For example, how much momentum does a 5 kilogram rock have if it's moving at 2 meters per second? Well, momentum is mass times velocity, so you take the mass of the rock, 5 kilograms, times the velocity, which is 2 meters per second, and you get 10 units. And the units of momentum are kilograms times meters per second. So that's how much momentum you have in this rock. Now I told you that a cannon shoots a cannonball forwards and therefore rolls backwards. So if a 700 kilogram cannon fires a 5 kilogram cannonball forward at 100 meters per second, how fast will the cannon itself be moving backwards? Now, notice that initially the cannon and the cannonball are not moving. Initially they are stationary. So we don't have to deal with a change of momentum. We can just deal with the momentum that it has at the beginning and the end. The momentum of the cannon is going to be equal to negative the momentum of the cannonball. Actually, I think I got that flipped. Yeah, I'm going to use this as the cannon. This is the cannonball. It doesn't actually matter which object is object 1 and object 2. It'll work whatever you choose. So don't worry about making sure the right thing is on the left and the right side. It doesn't actually matter. So we'll plug in those numbers. The mass of the cannon multiplied by the velocity of the cannon is equal to negative mass of the cannonball times the velocity of the cannonball. You can simplify this, and you calculate that the velocity of the cannon is negative 0.71 meters per second. So that's how fast the cannon moves backwards if it shoots the cannonball forward at 100 meters per second. The gun also has recoil. Normally when you shoot a gun, initially the gun and the bullet are not moving, so they're both stationary, so we can use our super simple equation. If a 5 kilogram gun shoots a .02 kilogram bullet at 250 meters per second forward, what is going to be the velocity of the gun's recoil? Well, we have our formula, where the final velocity of the gun is equal to negative, the momentum of the gun is equal to negative the momentum of the bullet. So, the 5 kilogram gun, we want to know how fast it's going. It shoots a .02 kilogram bullet at 250 meters per second. We plug in the numbers, we simplify, and it turns out that the recoil velocity of the gun is negative 1 meters per second. So that's how fast the gun recoils. Finally, rockets move fuel downwards, and that causes the rocket to move upwards. So, if we have a 30,000 kilogram rocket shooting 400 kilograms of fuel downwards at 100 meters per second, so it's downwards, this is probably going to be negative, how fast will the rocket be moving upwards? Well, initially the rocket is just stationary on the landing pad, right? We have the rocket initially just standing there, and then it shoots the fuel downwards and moves up. So we can use our simplified version where all of the momentum of the rocket comes from the momentum of the fuel getting shot downwards. We don't have to deal with changes, which is nice. And so we'll just plug in the numbers. This is the mass of the rocket. We want to figure out the velocity of the rocket. We know that the mass of the fuel is 400 kilograms, and the fuel moves downwards at 100 meters per second. So we simplify, and the rocket's moving forward at 1.33 meters per second. So that's all you need to watch. I want to tell you where the formula comes from. Why does it work? This is optional and sort of long. So let's say you kick a rock. Your foot comes to the rock moves away. That hurts your foot, right? Why does it hurt your foot? Well, because of Newton's third law. Every action has an equal and opposite reaction. So when your foot applies a force to the rock applies an equal and opposite force on your foot. That's why it hurts. So let's play with this a little bit. The force on the rock is equal to the negative force on your foot. Force rock equals negative force foot. Now F equals ma, so we'll substitute that in. F equals ma. We also know that acceleration is the change of velocity over time. So let's substitute that in. So now let's just make sure we know what all these mean. This is the mass of the rock. That's the mass of the foot. This is the amount by which the rock speeds up when you kick it. This is how much your foot slows down, because of the negative sign. So your foot slows down. And this is the time that the foot and the rock are in contact. And that's the same on both sides. So let's do a little bit more simplifying. Just getting rid of the parentheses here because they can be confusing. And if you have a number multiplied by a fraction, you can put that number on the top of the fraction. So let me do that. The last step is to realize that you're dividing by the same number on both sides, right? I'm dividing by the time, but the time that the rock is touching my foot is the same as the time the foot is touching my rock. So this is the same on both sides. I can multiply both sides of the equal sign by this t. So let me multiply both sides by t. And then it cancels. So now let's look at what we have. We have an equation that relates the change of speed in two objects. The change of velocity of the rock and the change of velocity of the foot. They are related with this negative sign. So the mass of the rock times its change of velocity is equal to negative the mass of the foot times the change of its velocity. And there was nothing special about the rock and your foot. This would work for any two objects that push each other. So we can call them object A and object B. So whenever two objects, call them A and B, interact, this relationship will hold. The equation is normally written like this, where we have the change of mass times velocity, because mass doesn't really change. So mass times the change of velocity is the same as the change in mass times velocity. This says that if object A gains momentum, so if the change of object A's momentum is positive, then the change of object B's momentum must be negative. So the other object must lose the same amount, which means that the combined amount doesn't change, because if this goes up by 5 and this goes down by 5, then if you add them together, they'll be the same number. So the momentum actually comes from Newton's laws, which is why maybe it seems familiar. Or more accurately, Newton's laws comes from the conservation of momentum. So that's where it comes from. That's how you use it. I hope this is helpful.